Okay, so good day everyone. So today we will be discussing or solving some of the sample problems that we have for variable separable differential equations. So let's have the list of all the examples that we will solve later. Let's start with the first example. The derivative of q with respect to t is equal to k multiplied to q minus 70. So again, this type of differential equation is a variable separable because we know that we can separate the variables with their respective differentials. So in this type of differential equation, we only have two variables, q and t, and the k here is a constant. So with that, let's have our differential equation equals k multiplied to q minus 70. We will multiply the whole equation by dt, okay, so that we can eliminate all differentials under the fraction bar. And we check if the differential t contains all variables t only, and the differential q contains all variables q only. But on this side of the equation, that is on the right side, we have q minus 70 here. So it means we will also eliminate this q minus 70 on the right side of our equation. So the result would be dq over q minus 70 equals k dt. And at this point, we can now say that the variables are in their respective differentials and we can eventually integrate. Okay? For this first integration, q minus 70, if we let u is equal to q minus 70, we can say that the derivative u is equal to dq. Okay? And we can formally say that the result would be ln of q minus 70 equals kt plus c. Okay? So this could be the final answer. But again, if you want to isolate your dependent variable here, so we can eventually, again, this is coined or accepted as your final answer. But we can isolate your q here by using the exponential function. So we have ln of q minus 70 is equal to kt plus c. Okay, if I raise, or rather e raised to the whole equation, that would be q minus 70 equals e raised to kt plus c. But eventually, this could also be e raised to kt multiplied to e raised to c. If I label my first c or constant or arbitrary constant as c1, I can say that e raised to any constant would also be a constant. So I could simplify this one into c e raised to kt. And by transposing the negative 70 on the other side, I have the explicit solution for our differential equation. That is q is equal to c e raised to kt plus 70. So that is our answer. So again, it can also be this answer. This is the implicit solution, and this is our explicit solution. Okay. Next example. Next is we have the derivative of y with respect to x is equal to xy plus 2y minus x minus 2 over xy minus 3y plus x minus 3. So again, at first glance, we cannot determine if this differential equation is already a variable separable differential equation. But the tip is that we must first factor out any common terms. So by factoring out any common terms, we have the derivative of y with respect to x would be equal to, for the numerator, we can factor out here y. That would be x plus 2. And for the second group, we can factor out negative 1. And that would be x plus 2 over. Okay, for the denominator, we can factor out again y. That would be left with x minus 3. And you have 1 here, x minus 3. And by using algebra, we can group the terms into y minus 1 multiplied to x plus 2 over y plus 1 multiplied to x minus 3. And in this case, we can now say that our differential equation is variable separable. Okay? So, what we need to do is we multiply the whole equation by dx. And since dx is on the right side, we must adhere to our rule that it is imperative na x is the only variable grouped with dx. But we have here y minus 1, so we will divide that. Same as true with y plus 1, we will multiply that to the whole equation. And eventually, we will have y plus 1 over y minus 1 dy equals x plus 2 over x minus 3 dx. And in this case, it is now separated. So we can integrate the left side and the right side. Okay, with this, since our degree of the numerator is the same with the degree of the denominator, the first technique to use with this integration is to use synthetic division. But again, it would take up time. Okay, so it means what do we need to do is we use the plus minus rule. Okay, so with this plus minus rule, our goal here is to replicate the term that we have in our denominator so that we can eliminate later on the numerator and the denominator. Okay, how could we do that? So again, we must have the same term as the denominator, so it means it should be y minus 1 also on the numerator. But how can we make the numerator equal this numerator? How can we make this numerator equal to y plus 1? Is that the result must be y plus 1 also. So it means it lacks plus 2. Okay. Why is that? Because again, actually you could just use your calculator here. Just have 1, then minus negative 1. Okay. Then that's it. That's plus 2. Or if you simplify the numerator, it will result into y plus 1. Okay. dy equals. Same as true with the right side. X minus 3. X minus 3. So again, that would be 2 minus negative 3. So we need 5. Okay, to make the equation the same. Okay, so next is to group the terms. We have for the first integration, that would be y minus 1 over y minus 1 dy. Then, okay, you have plus 2 dy over y minus 1. And for the right side, we have x minus 3. That is x minus 3 over x minus 3 dx. Then we have plus 5 integral of dx over x minus 3. And we can now integrate. This would be integral of dy plus 2 integral of dy over y minus 1 equals, this would be integral of dx plus 5 integral of dx over x minus 3. And our answer would be y plus 2 ln of y minus 1 equals x plus 5 ln of x minus 3. So since in this equation, we cannot isolate y, so it is imperative that we stay to this implicit solution, and this is our final answer. Okay, next. Our next example would be the derivative of p with respect to t is equal to p minus p squared. Okay, so again, what we need to do is to put all the variables p to its respective differential. First, we multiply dt so that we can eliminate any differentials under the fraction bar. Then we divide p minus p squared. Again, p here is a variable, not a constant. Okay? P is our dependent variable. Okay, so our result would be derivative of p over p minus p squared equals dt. And we can now integrate. Okay? In our integral of dp over p minus p squared, we can factor out p and 1 minus p. With this, since we have factors on our denominator, so we will use partial fractions. So for partial fractions, we have here 1 over p multiplied to 1 minus p. So we will assign a for p and b for 1 minus p. Cross multiply, that would be 1 is equal to a multiplied to 1 minus p plus b multiplied to p. If we let our p equal 0, we can eliminate b, and eventually we can find the value of a. So a is equal to 1. If we let our p equal to 1, we can eliminate a, and we can find the value of b. That would be also 1. So since a and b is equal to 1, we go back to our original equation. That would be integral of 1 over p plus 1 over 1 minus p. Okay, that would be dp equals integral of dt. Then regroup. That would be 1 over p dp plus, okay, for the denominator, in order to simplify further, I can actually factor out the negative sign. Okay. Then that would be integral of dp over p minus integral of dp over p minus 1 equals integral of dt. That would be ln of p minus ln of p minus 1 equals p plus c. I think I have... Okay, so I'll just go back to this. Okay, it lacks plus c. Okay? So reminder again, if we don't have a plus arbitrary constant, it means our solution is a singular solution. But again, your arbitrary constant is very important in order to determine that our solution is a general solution. It means we don't have any values for arbitrary constant yet. Okay? So this is the answer or the solution implicitly. But again, if you want to simplify further or you want to isolate P and make it an explicit solution, okay, we can eventually combine the natural log function. Since it is subtraction, so it means that would be P over P minus 1 equals T plus C. And that would be E, okay, raised to the whole equation. That would be P over P minus 1 equals C. Okay, I'll just skip the same process that we have on example number 1. That would be E raised to P. Okay, so again, it can be this answer or this on the bottom. Okay, so we have solved 3 problems already. Next, the 4th problem would be sine 3x dx plus 2y cosine cube 3x dy is equal to 0. Okay? So again, we rewrite the equation here plus 2y cosine cube 3x dy is equal to 0. Okay, so again, since we are solving variable separable problems, it means we need to make sure that our dx and dy has coefficients of x or y only, depending on their variables. So since for dy here, we have cosine cube 3x, so we will divide that on the whole equation. And our result would be sine 3x dx over cosine cube 3x plus 2y dy equals 0. And in this time, we can now integrate. Okay? So we can actually put our cosine on the numerator so that it will be later on a power formula. Okay? Or I can just put the negative 3 outside. Okay? Plus integral of 2y dy equals integral of 0. Okay, if we let u to be our cosine 3x, our derivative of u would be, so the derivative of cosine is negative sine 3x multiplied to the derivative of the inside function, which is 3dx. So your du would be equal to negative 3 sine 3x dx. And du over negative 3 would be equal to sine 3x dx. Okay? So that would be integral of u raised to negative 3. Then your sine 3x dx would be du over negative 3. Then plus 2, that would be y dy equals integral of 0. So this would be negative 1/3 multiplied to u raised to negative 3 plus 1 over negative 3 plus 1 plus 2 multiplied to y squared over 2 equals c. So your negative 1/3 divided by negative 3 plus 1, that would be 1/6. Okay? So 1/6 u raised to negative 2 plus y squared equals c. But again, our u is cosine 3x. So that would be 1/6 cosine squared 3x plus y squared equals c. So that is our final answer, implicitly. But again, if you want to extract the explicit solution for this, so it means, okay, this would be y squared equals c minus 1/6 cosine squared 3x. And eventually that would be y equals square root of c minus 1/6 cosine 3 squared 3x. So again, this is the explicit solution for number 4. And for our last problem or example, that would be this. Your derivative of y with respect to x is equal to e raised to 3x plus 2y. So we rewrite it here. Okay, e raised to 3x plus 2y. Since the exponents are added, it means the base is the same if you multiply. So that would be e raised to 3x multiplied to e raised to 2y. We can now separate our variables. That would be the x. And we divide the whole equation by e raised to 2y. The result would be e raised to 2y. Okay? Would be dy over e raised to 2y. Okay? Equals e raised to 3x dx. We can now integrate. That would be integral of e raised to negative 2y is equal to e raised to 3x dx. And eventually, we need negative 2 here. So that would be 1 over negative 2 e raised to negative 2y equals 1 over 3 e raised to 3x plus c. Okay? And, okay, if you want the simplest version, that would be negative 1/2 e raised to negative 2y equals 1/3 e raised to 3x plus c. So this is our answer. This is our implicit answer. But again, if you want to isolate your y here, okay, we rewrite it again. Negative 1/2 e raised to negative 2y equals 1/3 e raised to 3x plus c. Okay. We multiply the whole equation by negative 2 so that we will have e raised to negative 2y equals, that would be negative 2/3 e raised to 3x. And again, we'll make this as our c1 because any constant multiplied to negative 2 would be constant. Okay? Plus c. Okay, next. We take the natural log of the whole equation. Okay, that would be negative 2y equals natural log of negative 2/3 e raised to 3x plus c. Okay, so Okay, how can we eliminate the natural log here? So actually, there's a clue here. So that would be negative 2y. Okay, I will factor out your negative 2/3 first. So again, if I factor out your negative 2/3, I'll make this as my C2. So it will just be a constant. Okay. I want to make this constant e raised to that constant so that I can combine the exponential function for this. So that would be negative 2y equals ln of. That would be negative 2/3 e raised to 3x plus e raised to c. This would be c3. And eventually that would be negative 2y equals ln of negative 2/3. Okay. This would be e raised to 3x plus c. Okay. Okay. So next is that for your negative 2/3, what do we need to do here is, okay, ln of negative 2/3. Okay. So since it is multiplied, no, that would be negative 2y equals ln of negative 2/3 plus, that would be ln of e raised to 3x plus c. Okay? And eventually, that would be negative 2y equals ln of negative 2/3 plus e. Okay? This would now be 3x plus c. So again, your ln of negative 2/3 is a constant, and we combine it with another constant, so it means we'll make this as our c4. And eventually, that would be negative 2y equals 3x plus c4. Okay, this would now be c. And our final answer would be y equals, because we divide a negative 2 to the whole equation, that would be y equals negative 3 halves x plus, this would be c5 because we multiplied negative 1/2 to it, c. So this is the explicit solution to our implicit solution here. Okay, so those are the final. So again, take note that you can have this as your answer. Okay, if ever there are choices in the exam, and this is one of the choices. So it means you need to make your answer the same as that of the choice. Okay, so thank you so much, and God bless.